My speech will be about instrumental odor monitoring systems, so e-noses applied for environmental odor monitoring, so that are commonly defined like this, IOMS, and especially I will focus on their testing and performance evaluation. First of all, I would like to say that, forgive me, but I tend to use the terms e-nose, electronic nose, and IOMS absolutely as synonyms, although they should, IOMS is a more generic term, but consider that during this presentation, when I talk about IOMS and e-nose, I mean the same thing. So first, a short introduction of my research group. I am an associate professor at Politecnico di Milano, which is the largest technical university in Italy. I am part of the olfactometric laboratory research group at the Department of Chemistry, Materials and Chemical Engineering. And personally, I've started working, I was the first one initiating the research with e-noses at Politecnico in 2003. Because of the research background and the activities of olfactometric laboratory, our activity with the e-noses was mainly focused on environmental odor monitoring. Only recently, we have expanded our research activity related to sensory analysis also to other fields like medical diagnosis and process control. But really, we have a huge experience with all what is related to odor measurement and odor monitoring in the environment. And I've participated to the technical working groups of CEN, Working Group 41, which was presented in a previous meeting by Ton van Arreveld. And I also took part to the UNI working group, the Italian group, who was presented by Domenico Cipriano a couple of meetings ago. So I don't think that I have to teach anybody here in this group what an e-nose is. So I suppose that's, you know it better than me. I just want to focus on why it is so interesting for environmental odor monitoring. There are a lot of methods that can be used to measure odors in their environment. However, the e-nose is currently the only instrument that is specific for odor analysis. So it allows the continuous analysis of ambient air. According to the definitions that have been provided both in the CEN group and the UNI group, we can distinguish three types of main applications of e-noses for environmental odor monitoring. Odor detection, whereby the e-nose is used for detecting the presence or absence of odor. Odor classification, for the recognition of the odor provenance. And odor quantification, which is related to the possibility to provide a metric that is somehow correlated to the measurement of the odor concentration. And I would say, that the electronic nose is particularly interesting because compared to dynamic olfactometry, which is a quantitative analysis, or field inspections and so on, it is the only method that is really capable to provide information about odor quality and odor class. Another brief introduction about the Italian context. In Italy, we don't have yet a national regulation regarding odor pollution management. However, we have several regional guidelines and regulations which more or less have been all inspired by the regional guideline of the region of Lombardy, which is the region I come from, which was issued in 2012. And the gold standard method for odor impact assessment in Italy is olfactometric analysis followed by dispersion modeling. However, if there are people familiar with the dispersion models in this group, you might know that their application to other sources is not always possible because of the existence of diffuse emissions, because of variable emissions. For instance, because of discontinuous production, like it is the case for the production of bitumen, for instance, or also for in the case of productions on order, like it is the case typically for pharmaceutical industries. So it is very difficult to be able to quantify the source in detail. In such cases, the use of electronic noses can be extremely interesting because they do not need a precise quantification of the source for a whole year, but they can be used for direct odor impact determination at the receptors. And that is, let's say, the main use of electronic noses in Italy. That has been the main use of electronic noses in Italy over the last, I would say, 10, 12 years. However, more recently, also the application of IOMS or e-noses at plant fence line has been growing a lot. There are an increasing number of applications in which e-noses are installed at plant fence line, especially in the cases of waste treatment plants and landfills, for the continuous measurement of the odor concentration. And in some cases, which is really interesting, they have started being prescribed in environmental permits. So there are some existing plants and some new plants which are forced, let's say, to install e-noses for the continuous measurement of odor concentration at their fence lines. And that is exactly the reason why there is an urgent need for standardization, especially in Italy, probably also in other countries as well. When IOMS e-noses start gaining a legal value, because their results can be used for basically closing a plant, then it becomes clear that precise rules for qualification of those instruments become fundamental. Domenico Cipriano and I wrote a review about the standardization approaches over the last 20 years, a couple of years ago. And as you know, in Italy, we have, as Domenico presented, now a technical standard, UNI, regarding the qualification of e-noses, of IOMS. However, instead of talking to you about standards, which you have already heard of from other people who are more expert than me, I would rather describe to you what we have done as research activity, as monitoring activity in our lab, in our research group. As I told before, we have started working with electronic noses for environmental odor monitoring several years ago. And what we did at the beginning, which has already also been published in previous publication, was training the instrument, then install it somewhere at a receptor close to some odor emitting plant, wastewater treatment plant or landfill or composting plant or whatever. Let it there for a couple of weeks or a month, or let's say a mid-short period of time. Then finally the data recorded during the monitoring were processed in order to provide an information about the frequency of detection of odors of a certain plant, about odor classification and so on. And the only validation that was done at the end by comparing the results of the outcomes of the IOMS with other observations or with the dispersion modeling results and things like that. But we soon realized that this scheme was not sufficient. And so we introduced some extra steps in our procedures. The first preliminary laboratory testing step, and to be carried out before the training, before even knowing where to go, and a performance verification step to be carried out in the field before the monitoring starts, so after the instrument has been trained. Let's start with the laboratory testing. Let me say that this has been a crucial, very critical issue both at the SIGN group and also in the UNI group, because we are all aware that what is really important is the validation in the field, the verification in the field. However, and so someone criticized that this preliminary laboratory testing might be useless. However, I am not of this idea for one simple reason. We know that currently there are a lot of different commercial instruments on the market that are sold for environmental monitoring purposes. Instruments of different shapes, sizes, technologies, and prices, of course. Since personally I do not produce electronic noses in my lab, will help in developing them, but we do not sell electronic noses. What we typically do is buying them. And when I buy an instrument, I usually would like to know if I'm spending my money well or not. So, in our opinion, it was very important to let's say, to develop a procedure in order to be able to compare different instruments, different technologies before they are installed in the field, and in some cases prior to purchase. And this, of course, can only be done under reproducibility conditions. So that is why we started thinking about some sort of testing procedure for comparing different instruments. So in our idea, laboratory testing is something that provides preliminary information about e-noses that we would like to apply for environmental odor monitoring. What can we determine in the lab? What can we base our comparison on? Well, we can compare different instruments in terms of sensitivity, meaning the lower detection limit towards specific odors or specific substances, repeatability of responses, which is also an important aspect, stability of responses under conditions of variable temperature and humidity, which typically occur in environmental odor monitoring, because typically instruments are installed outdoor where conditions may change drastically. And then they can be compared also in terms of odor detection accuracy or classification accuracy. We published something about that in the past. Let's say that our main article about this was published in 2016, and there we did something that I would probably not do anymore today, meaning that in this study we decided to carry out some tests using pure compounds, and we chose these pure compounds among those compounds that we thought were that we knew were most representative of the environmental emissions that were more interesting for us. And we decided to use acetone as representative of oxygenated hydrocarbon, ammonia as a nitrogen compound, dimethyl disulfide and hydrogen sulfide as sulfur compounds, ethanol as a representative of alcohols, and limonene, which is a terpene which is typically present in vegetable degradation processes. However, to be very honest, as we also discussed in the previous meeting of the previous meeting of this working group, probably it would be better, probably for sure it would be better not to use pure compounds, pure substances, but to use mixtures, some sort of synthetic odor samples. However, that is how we approached the problem 5 years ago. And despite the fact that using pure compounds is not the best solution, I am quite convinced that we were able to acquire some interesting information about the instruments that we tested. In our case, we we tested two different instruments. One is the SACMI EOS Ambiente, which is thought for be applied at receptors mainly, and the other one is the Rubik's WT1, which is more designed for use at fence line, for fence line monitoring, and they are very different instruments, I should say. We compared them in terms of lower detection limit, and the lower detection limit was expressed for the different substances, both in terms of ppms, but also in terms of other units, because in the end, what we are interested is not just the chemical concentration at which the instrument is able to provide a response, but how much this concentration is related to the perception by humans. So, for instance, for hydrogen sulfide, given that hydrogen sulfide has a very, very low odor threshold concentration, it is clear that despite having lower detection limits, this is still quite a lot higher than the concentration at which humans start to perceive hydrogen sulfide. It is clear that this information is only partial, because we know that in environmental odor monitoring application you might experience correlated detection. So you might be able to detect the presence of hydrogen sulfide not by directly sensing hydrogen sulfide, but by sensing something that comes together with hydrogen sulfide. But on the other hand, this gave us a first preliminary information about the sensitivity of the two instruments. The repeatability was evaluated with this expression, so based on the standard deviation of the responses to the same stimulus. And then also we compared the instruments in terms of detection accuracy. What do we mean by detection accuracy? It means the accuracy in the classification of absence of odor and presence of odor without distinguishing a particular different odor classes. So here it's really the distinction between no odor and odor. And here, of course, what we did is correlating. So how did we define the no odor and odor conditions? With our panel. We have an olfactometric laboratory, so we have panelists, and we are able to define when a sample is below its odor concentration threshold or above the odor concentration threshold. And we see that the two instruments have very good detection accuracy indexes. The detection accuracy is slightly higher for the SACMI instrument, but as we said, they are thought for different applications, so that is okay, that is correct, that they have such different performances. And what we further did was trying to check their classification accuracy to the substances that we analyzed. And here we decided to make this evaluation by defining 3 levels of concentration, where low is very close to the lower detection limit of the instruments towards the compound. Intermediate is about 5-10 times higher than the lower detection limit, and high is a higher concentration. And so we see that, of course, by working with higher concentration, typically the accuracies become much higher. Finally, another type of test that can be carried out in the lab is the check of the capability of the instrument of still providing reliable responses when temperatures and humidity change. So what we did is to change the relative humidity in the lab from 40% to 80%, And then we varied the temperature from 15 degrees to 25 degrees, and we did permutation of the different combinations of temperatures and humidity. And so we were able to check, to verify the number of correct classifications that the instrument gave for each of the target compounds and for each of the conditions tested. Now, without commenting too much the numbers, which is not the scope of the presentation of today, this was more or less to tell you what we usually try to do in the lab with an unknown instrument. Now, as I said, not with pure substances anymore, but with the mixtures of compounds. Of course, this type of evaluation can be replicated as such with environmental samples collected directly on the plant under investigation. This provides, of course, results that are much more related to the specific application, but this means that to compare instruments, you need to have exactly the same samples. And so this is one of the points. So this is what the type of tests that we carry out for the characterization of E-noses in our laboratory before we go into the field. But then I said the important step is basically the performance verification in the field. And here I decided to, and what do we mean with that? We mean that once the instrument has been trained for the specific application, it is installed where it has to be installed, and there we start doing field tests that should be carried out in conditions that are very close to the real working condition of the instrument. So to provide information about the specific monitoring conditions. So basically what we do is at this point to collect samples at the plant, and that should be samples, of course, independent, totally independent, new samples, and not the same samples that we use for the training, of course. And by testing, by analyzing these samples, which have to be diluted, as we will see later, we are capable to verify the performance of the IOMS in terms of what? In terms of lower detection limit towards the ODOURS under investigation, in terms of accuracy indexes relevant both to detection and classification, and also in terms of limits of acceptance for Odour quantification performances, if Odour concentration measurement is the desired output of the E-nose. And here I want to present two very different case studies. The first one relates to the monitoring of a tire storage area. And here in this case, the aim of the monitoring was a qualitative recognition of the odor. So the idea here was to detect the presence of odors from a tire storage area, and thus also recognize that it was an odor coming from the tire storage area and not from somewhere else. This has been published last year in Atmosphere. So if you want more details about this study, you can find them in this paper, which is open access, but I will shortly describe it here. We have this huge tire storage area with the residential area, which is very, very close to the plant. So we decided to install an electronic nose at the plant fence line, to be honest, but it was so close, it was like 20 meters from the receptors. So for us, this installation point was representative of what the receptor perceived. And here we used the SACMI EOS 507 instrument. Why is it so interesting? Well, this is how the situation looked like. This is a typical case in which dynamic olfactometry and dispersion modeling are not applicable, at least not at the current state of the knowledge. And believe me, we are doing a lot of research in order to characterize the most complex sources you could ever imagine. However, this is really something that is cannot be sampled with wind tunnels, flux chambers, or whatever you might think of. And it is so variable over time because, of course, the tire storage area is super full in the months of September and April, when typically tires are changed from winter to summer season, and the situation is completely different in the other periods. So it's really something that cannot be modeled in a reliable way. So in this case, the use of the electronic nose was really the only solution applicable in order to get an information about the presence of odors at the people houses where people complained. And by training the instrument, we could see that the two odors, that air and the odor of the tires could be very well distinguished one from the other, or even at very low odor concentration. Indeed, one of the problems that we had in this plant was that the odor concentrations of the emissions were extremely low. I would say, almost never measured odor concentration above 80 odor units per cubic meter at the source, which is really very, very low. So here the challenge was being capable of detecting the odors at low concentrations. So once we had trained the instrument, we installed it, as I showed you, at the plant fence line, and we started our field performance testing. As a first thing, we started, so we basically collected samples from the emissions, then diluted them or not, because in that case, dilution was not so necessary. And we replicated the tests in different days in order to account for different meteorological conditions, and so in some way also account for different conditions of temperature and of humidity. The first day was a typical hot and sunny day, like 25 degrees, sun, fantastic, low relative humidity. The second day was cold, it was like 10 degrees Celsius, foggy and rainy. So really, we tried to catch to extremely different conditions to do our tests. What we could see is that the instrument classified correctly the odors above concentration of 30 odor units per cubic meter. Below these odor concentrations, these are the measurements in red, the instrument misclassified the odors. This resulted in an accuracy in the index of 86% and in the following confusion matrix. What we did then, well, the monitoring, we did a continuous, but I mean, the focus was this one. So the testing in the field, what we did was really to provide to the instrument alternating samples of air and of tires odor to see in which condition the instrument classified the odors correctly. So this is the field performance testing. Just to close the case study, we then started the monitoring, which lasted 45 days, and we recorded all the events at which the instrument recognized, detected the presence of odors of the tire storage area, which resulted in about 5% of recognitions of odors attributable to the plant, which is usually considered as to be acceptable, although, as I said, there is no specific regulation determining what is acceptable and what is not. But let's say that below 10% it is considered to be acceptable. The second case study is completely different.
Sorry,
Yes.
Laura, to interrupt, because we want to have some time for questions, and I'm pretty sure it's a very interesting talk, so people have questions. Could you please conclude in maybe 5 minutes last?
Yes, it's almost finished. So don't worry, no more
Great.
than another 3 minutes, I promise.
Okay, great, thank you.
So this is the second case study. It is about a landfill, and here the point was not to classify odors, but just to, but not just, but to measure the odor concentration continuously at the plant fence line with, in this case, a Rubik's WT1 instrument. So we trained the instrument to recognize the different odor classes of the landfill, and sorry, it would help if the slides worked. And what is important here is that to develop a quantification model with the INOS, we developed what we call a multi-phase decisional model, meaning that the instrument first classifies the odor and then carries out a regression on the points relevant to the class that has been recognized. This is, as I will show later, the only way to obtain a reliable quantification of the odor in terms of odor concentration. So first, the odor has to be recognized, classified correctly, and then the regression model can be carried out. The field performance testing, again, involved the collection of new samples at the source, their dilution, their olfactometric analysis, their dilution, and their analysis with electronic nose, and then performance evaluation. The problem here is how to carry out performance evaluations. Here we reported the odor concentration, the different samples with the odor concentrations measured by dynamic olfactometry, which is the full point, and then the little star is the odor concentration estimated by the IOMS. I mean, this looks good, but how to quantify how good this is? And here we have a serious problem. And the problem is that in this case, the reference method, which is dynamic olfactometry, has a very high measurement uncertainty. And as Santiago Marco taught us, in this case, regression methods are not suitable, but we shall use model comparison methods in order to provide information about the performance of the IOMS. And this has been, again, a long discussion into the SAN group. Into the SAN group, indeed, another more conservative approach was preferred, to be honest. But in this case, we decided to propose the approach that Santiago Marco, who is a member of the SAN group, proposed, which is the Bland and Altman approach. Without getting too much into the description of this, the Bland-Altman approach allows to determine the upper limit of agreement and the lower limit of agreement of the techniques. So expressing, and we can see that these are as expressed as factors. And again, I do not want to say it's much, it's okay, it's good, it's bad. The important thing is that by means of this method, it is possible to quantify how good is the agreement between dynamic olfactometry and IOMS results. And it is quite clear that well, here we wanted to compare the two models, one that carried out the quantification without previously classifying, and it is quite clear that with this model that first classifies and then quantifies, we got much better results in terms of agreement between dynamic olfactometry and IOMS results. This is what we did afterwards. So these are the results of the monitoring, and we could see that every time that we could very good see that there is a strong correlation between the peaks of odor concentration measured by the instrument at the plant fence line and the occurrence of odor events at the receptor. I am also a dispersion modelist, so I'm totally aware that these types of correlation should be further put in relation with meteorological conditions, wind directions, and atmospheric stability. This is the next chapter, of course, and I hope I will present it in another occasion. To conclude, INOSEs are extremely interesting and effective tools for environmental odor monitoring. Standardization is really much needed because there are a high number of instruments on the market and there are a lot of degrees of freedom in their utilization. In particular, quality protocols are needed in order to verify the instrument performance and thus enable the comparisons of different instruments, quantify the main characteristics of the instrument, and also provide information about the measurement uncertainty. We know that this is not this is challenging. It is not an easy task. However, my opinion is that the current status of the technology seems to be sufficiently mature to undergo such a process, and otherwise we wouldn't be here. So thank you very much for the attention. I'd like to conclude with a citation, which is, what is not measured cannot be improved, and I like to think about that as the electronic nose performance. So we need to measure it in order to improve it. Thank you again.